All right, let's dive into something really cool, one of the most powerful tools we have for predicting the future. It's called a temporal point process. We're going to go on a little journey, starting with simple statistics and going all the way to some of the most cutting-edge AI to see how we model when things are going to happen. So this sounds like the beginning of a weird joke, right? You've got a natural disaster, something blowing up on social media, and a simple online purchase. On the surface, they seem totally random, completely unrelated. But are they? You guessed it. The common thread here is time. See, none of these are just isolated incidents. They're all points in a sequence. And the real magic, the secret to prediction, is understanding the complex, often hidden rhythms of when these things occur and, crucially, how they influence each other. And there's a name for the tool we use to do this. A temporal point process, or TPP for short, is basically the formal language for talking about these event sequences. It gives us a solid, mathematical way to describe, and more importantly, to predict the flow of all these seemingly random events. Now, what's so interesting is that TPP isn't just one single model. Think of it more like a whole family of models that has been growing and evolving for decades. It's kind of like a tree, you know? The roots are in classic statistics, but the branches are now reaching way up into the most advanced AI we have today. So let's trace that evolution. So let's start at the beginning, right at the foundation. We're going to look at the original statistical models that really laid the groundwork for this entire field. These were the first attempts to find some kind of order in the chaos of random events. In the early days, there were two big players. First, you have the Poisson process. It's super simple. It just assumes every event is completely independent, like random raindrops falling from the sky. One drop has no idea when the next one is coming. But then came the Hawkes process, and this was a huge leap forward. It was built on the idea that some events can actually cause other events. Just like a big earthquake can trigger a whole series of aftershock. And this idea was called self-excitation. That was the breakthrough. It captures the fact that past events don't just happen and then vanish. No, they leave a ripple, an influence that makes future events more likely to happen. This was the key that finally unlocked our ability to model real-world chain reactions. But of course, there was a catch. These classic models were, well, a bit rigid. You had to spell out the exact mathematical formula for them to follow. And that worked okay for some simple cases, but the real world is messy, it's complex. Its patterns are way too wild to be crammed into some predefined equation. They needed something with more flexibility. And that flexibility, well, it arrived in a big way with the deep learning revolution. This was the moment AI really learned to understand the nuances of time, and it completely supercharged the whole field of event prediction. So the big shift was this. Instead of us telling the model what to look for, we just let the data speak for itself. Instead of trying to force events into a rigid mathematical box, these new neural TPPs use neural networks to automatically discover all those complex, hidden patterns on their own. And that gave them way more power to model what's actually happening in the real world. And this new approach really branched out into three main flavors. First, you've got recurrent models, or RNNs. These kind of think like we do. They process events one by one in order. Then, the autoregressive models, which you might know from Transformers. These guys have a superpower. They can look at the entire history of events all at once to see the bigger picture. And finally, there's a third approach that uses differential equations to really focus on the continuous flow of time between the events. And this table really gets at the fundamental trade-off, especially between the two most common approaches. It's kind of like the nimble sprinter versus the marathon runner with a perfect memory. On one side, you have the recurrent models. They're the sprinters. They're really efficient, they're fast, but they have a pretty short memory. They can't easily see long-range patterns. On the other side, you have the autoregressive models, like Transformers. These are the marathon runners. They are absolute heavyweights. They can see the entire history, they pick up on those long-range connections, but all that power comes at a much higher cost to train. So it's that classic engineering choice. Do you need speed or do you need power?
But guess what? The evolution didn't stop there. We're now entering a whole new era, a new frontier, where the most powerful AI models on the planet, large language models, are actually learning to predict timelines.
And this is an absolute game changer, because LLMs don't just see a timestamp and an event category. They have a rich contextual understanding of the world. They can read the text, they can see the images, they can understand the meaning behind an event. It adds a whole new dimension to prediction. So how in the world does that work?
Well, to put it simply, you basically take everything about an event, the time it happened, what kind of event it was, any text or images that went with it, and you translate all of that into a special language of tokens that the LLM can understand. You feed it this whole story, and the LLM uses everything it knows to predict not just what might happen next, but maybe even why it will happen.
And here's where you can really see that power in action. In this example, the model isn't just looking at when a comment was posted on a video. It's actually reading the text of the comment, it's seeing the exact image that was on the screen at that very moment, and it's fusing all of that information together. It's making its predictions based on a complete contextual understanding of everything that's going on.
Okay, so this theory is all pretty fascinating, but let's get to the so what. What does this actually mean in the real world? Why does this powerful technology even matter? Let's look at a few applications.
Take social media. TPPs are absolutely crucial for modeling how information, and misinformation, spreads like wildfire. By understanding the timing and the triggers of posts and shares, these models can help us spot coordinated fake news campaigns right as they're starting to bubble up.
Or think about cybersecurity. It is all about finding patterns. TTPs can analyze the sequence of events in a cyber attack. Figure out the causal chain, like what tiny little probe led to which massive system breach. And that allows us to build much smarter, more proactive defense systems. And of course, in e-commerce, it's all about predicting what you're going to do next. By modeling your past clicks and purchases as an event sequence, these systems can predict not just what you might want to buy, but precisely when you're most likely to actually want to see that recommendation. But of course, the work is far from done. Researchers are still tackling some really big challenges. First up is model interpretability. How do we make these complex black boxes more transparent so we can actually understand and trust their predictions? Then there's scalability. How do we get these things to handle absolutely massive sequences of events without breaking? We also need better sampling efficiency, which is just a fancy way of saying we need to generate predictions way faster for real-time use. And finally, multimodal modeling, getting even better at weaving together text, images, audio, and all sorts of complex data into one single prediction. So here we are building these incredibly powerful tools for predicting not just what's going to happen, but when. And as this technology gets smarter and more precise every day, it leaves us with probably the most important question of all. What should we ask it next?